Okay, so today we will continue our lessons on chapter 7. Okay, so let me share the slide. Okay, so this is the topic, rotational kinematics and energy. So the word is rotational kinematics and energy. So rotational means rotations. Comes from the word rotations. That means pusingan. Okay, and how about kinematics? Kinematics is about motion. So motion in circle, motion in a form of rotations. Okay, motions in the rotations or motion in circles together with the energies. So this is chapter 7, and the chapter 7 will consist of a few sub chapters such as angular positions, velocity and acceleration. Okay, if you look carefully, this is not the same as what we learned in the kinematics because this involves the words angular, angular position, angular velocity, and angular acceleration. Okay, but basically we must base on whatever we have learned in chapter 2, which is the kinematics. Okay, try to imagine that you are going to learn some things that related to the kinematics but in rotations. Okay, and after that, okay, we will look further what can we do to the angular position, velocity and acceleration, but in terms of equations. Okay, in terms of equation. For example, what happens when we learn in motion, whenever the acceleration become constant, so we can produce or we can use some equations involved. So we're going to learn in the rotational kinematics part. Alright, and then we can see the connection between the linear and the rotational quantities. So today we're gonna finish all these sub chapters within 1 hour. Okay, it's a simple things. Okay, so let's start with the angular positions, velocity, and accelerations. So the angular position is known as theta. Okay, angular position is a theta, while theta is what? The angle. Okay, the angle measured from the reference line. If we say the reference lines here, okay, during this part is the x-axis. So the reference line is the x-axis with the unit SI unit of radian. Okay, radian, which is a dimensionless. Okay, and of course we look at theta when it becomes when it's greater than 0, when the theta is a positive value, it means counterclockwise rotation. Okay, theta is a counterclockwise rotation, have a counterclockwise rotation whenever it is a positive. While if the theta is negative, that means it rotates clockwise. Okay, so positive counterclockwise and negative will become clockwise from the reference line. So we are saying that the our reference line is an imaginary line such as a positive x-axis. Okay, so one full rotation, okay, one full rotation is called one revolution. Okay, so one revolution is one full rotation. Okay, that means one full rotation is equivalent to 360 degree, okay, in terms of degree, and at the same time in terms of radian is equivalent to 2 pi radian. So that means this one is in degree, this one is in radian. So you should differentiate between the value in degree and also in radian. Okay, because radian is the same as the degree, it have its own properties. Okay, because when we measure, when we talk about theta, okay, theta, I know some of you may noted this one as an angle, okay, angle, but that one is in force, okay. When we want to find the direction, so we have to find angle, which is theta. We need to find theta, which is the angle. So that means the angle will tell you the directions. But in the topic of angular position, for example, the angular position will also use theta. Okay, we'll also use theta. That means the angular position. Angular position. So theta is also equivalent to angular position. Why they talk about angular? Angular comes from the word angle. Okay, it means position with some angle. Position with some angle. So that what it mean by angular position. Okay, angular position. So can you see what is the meaning or the true meaning from the figure itself? Okay, look at this figure. Okay, right. So this is where the reference line. Okay, this is where the reference line, and you can see that the angle is calculated from the reference line until this point. So we are saying that this one is the theta initial and this one is the theta final. So delta theta is equivalent to theta final minus theta initial. That means the angular position. Okay, we cannot say that this is the length. Okay, because this is some arc. Okay, arc. Okay, lengkok. Okay, so it is not possible to say that this is the length between theta 1 and theta I and also theta f. So we are saying that from theta I to theta f is some arc, and that arc is equivalent to delta theta. Okay, that means delta angular position, right? So this is why I'm going to say just now is about arc. Okay, that means the length between theta final and also theta initial is equivalent to some value, some value, or that's also we call as arc length, panjang lengkok. Okay, panjang lengkok. That means it is not the same as the length, but it's arc length. The arc length is given by the equations of r theta. Rs equals to r theta. Okay, this one is you have already learned these things during your admaths. Okay, during your admaths in your school days, that s equals to r theta, and you need to measure theta in radian. Okay, for to get the value of s. So s equivalent to r theta. R is the radius, while theta is the angular position. Okay, theta is an angular position. Okay, all right. So in here, okay, the meaning of the theta is angular position. Therefore, the theta, the SI unit for theta is radian. Okay, radian. So we often use theta as radian, not as degree. Okay, but we can know that, okay, with our preference in radian, we can also measure theta in terms of degree. So meaning that, okay, maybe some question will give you some theta in degree. So you need to convert it to radian in order to solve the arc length. Okay, so meaning that one revolutions is equivalent to 360 degree, that is also equals to 2 pi radian. That means if you want to find 1 degree is equivalent to 2 pi divided by 360 degree. Okay, so let's say if you want to find what is the 30 degrees, so 2 pi over 360 degree times 30. So then in this case, you will get the value in radian. Okay, so if you want to calculate whatever you have in 1 radian, for example, okay, 360 degree is equivalent to 2 pi radian, and 1 radian is equivalent to 360 degree divided by 2 pi. Okay, how about 2 radian? Okay, so that means this one you times with 2. Okay, if 2 radian, then 360 degree 2 pi times 2 radian, or times 2, right? For example, times 2. So that is how you calculate and you measure theta, or you measure radian, and you measure theta in terms of radian or degree. Okay, so look at how the possible things when we discussing about angular position. Okay, so next is the angular velocity. Okay, angular velocity is the W, but this is not W. This is what we call as omega. Omega. Okay, so we often call it as omega, not W. Okay, if I heard W, this is wrong. But if you want to tell others, angular velocity is omega. Okay, and omega is equivalent to the average angular velocity. So the same happen when we have V equivalent to S over T, or maybe you want to write down as D over T. So this also happens, this is also happens in angular position and also angular velocity, because omega is equivalent to delta theta over delta t. That means change in the position over change in time. Okay, again, okay, it also involves time. Right now we have a change in angular position, and this one is change in time. Yes, we're still using time. And of course, the unit for angular position is radian, while the unit for time is seconds. So the SI unit for the omega will be radian per second, or radian second negative 1. Okay, you can write either one. Better to write down as radian per second or second negative 1. Okay, and the instantaneous angular velocity is given by omega delta theta over delta t here. And the limit is when delta t approaching 0. That means the delta t cannot be 0, but it towards 0. Okay, so in order to get the instantaneous angular velocity, it's the same thing happen when we want to calculate the instantaneous velocity. The instantaneous omega is equivalent to the instantaneous velocity, but right now we are using theta. We are using theta instead of delta d, or displacement. Okay, right. Okay, for example, this is one equation, one simple problems. Okay, an old phonograph record rotates clockwise at 33.5 RPM. Okay, the words RPM you will see a lot in this chapter, because RPM can be also noted as revolutions per minute, or maybe round per minute. Okay, we often use RPM. So when you look at the maybe at some device where they have 10,000 RPM, that means 10,000 round per minute. In 1 minute, it accelerates to 10,000. Okay, so that is what we mean by RPM. Okay, so the question is, what is its angular velocity? So they want to find omega in radian per second. Okay, in radian per second. So in again, this is 33.5. If we look carefully at the round per minute, that means, okay, this one is theta, this one is minute in time. So that means it's already in omega. But the questions wants you to uh, uh, to to get it with to get the answers. Okay, not in round per minute, but in SI unit. Its SI unit is radian per second. Okay, radian per second. So you need to convert it to radian per second. Okay, remember? Negative 33.5. Why negative? Because the phonograph rotates clockwise. Okay, the phonograph rotates clockwise. That means theta is below 0. Okay, because when it rotates clockwise, the theta will be less than 0. So that means you need to get it negative. Okay, the negative value, right? Because when the rotation is counterclockwise, theta will be positive. Therefore, the RPM will be positive. So in here, the theta is negative because of it rotates clockwise. Okay, negative 33.5 round per minute. That means revolutions per minute. Look at how they try to convert it from round per minute to radian per second. Again, revolutions, we put it, okay, on top of at the numerator part. Okay, and we know that one revolutions, okay, is 2 pi rad, so we can cancel out revolutions to revolutions, and we want to cancel out minute at the denominator part. So we put that 1 minute is equivalent to 60 seconds. So 1 minute we put it at the numerator, so that we can cancel out. Okay, when we want to cancel out, make sure we must cancel from the numerator to denominator. From denominator to denominator, side by side, you cannot cancel out. Okay, if you want to cancel out, we must cancel out with the top and bottom. Okay, top and bottom. Right, so that what's left is negative 33.5 times with 2 radian, 2 pi radian, and divide by 60 seconds. So you will get negative 3.49 radian per second. Okay, B, if a CD rotates at 22 radian per second, what is its angular speed in RPM? What is its angular speed in RPM? Okay, if the omega here, okay, from the units itself, we can know this is omega, okay, and you know that the theta will be greater than 0 because the value is positive. What is this angular speed in RPM? So 22 radian per second. So 2 pi radian over 1 revolution. So you can cancel out, and 1 second is going to be cancel out with the 60 second over here. So 22 times 1, okay, revolutions over 2 pi times 1 minute. So you will get 210 round per minute. Okay, you can try on your own in order to get these answers. Okay. All right. So with that case, we are now going to define one revolutions. Okay, the delta theta is equivalent to 2 pi. Okay, one delta theta is equivalent to what? In one revolutions, delta theta is going to be defined as 2 pi. Okay, if it's half the rotations, then delta theta is just pi. Okay, so one complete revolution is considered to be one period. This is what we call period. The capital T is not time, but it's called period. The unit for period is also seconds. Period means one complete cycle. Okay, this is what we mean by one complete cycle. Okay, so period is the time taken for one complete second. Okay, what time taken for one complete cycles. So in here, we are saying that the omega is based on delta theta over delta t. And we noted that in one revolutions, delta theta is 2 pi, and the time taken, okay, the time taken for one complete oscillation is one period. So therefore, from omega 2 pi over t, now we have another equations. Okay, one thing about this chapter is this involve a lot of equations, but not all equations are given in the appendix. So sometimes you need to derive it. Okay, so we are now saying we can define one period is equivalent to, okay, 2 pi over omega. Okay, 2 pi over omega, where the omega is the angular velocity. Okay, 2 pi means one complete cycles. Okay, sorry, 2 pi means one revolutions. All right, and omega, when, okay, just substitute with omega to t, and then of course the unit for period is second. For examples, the questions: find the period of a record that is rotating at 45 round per minute. Again, okay, we must you must consider to to have a better, or to have a, you have need to master how to derive, how to convert from one units to another units. Okay, so in this case, find the period of a record that is rotating 45 round per minute. Okay, 45 round per minute. Okay, round per minute. So you need, or sometimes we can got 45 revolutions per minute. So then one revolution is 2 pi rad, so you can cancel out minute with minute, then again you will get 4.7 radian per seconds. But the question now, you want to find period, not to find not to know that the value of omega. Okay, because omega is given in 45 round per minute, but 45 round per minute is not an SI unit. Remember, when we calculating rotational kinematics, we must calculate in SI unit. For example, theta is radian, omega is radian per second. Okay, now afterwards we will look at the angular acceleration. But okay, the time or the period here is 2 pi over omega. 2 pi is 2 pi rad. Okay, so omega is 4.7 radian per second. This is why we need to emphasize on the usage of SI unit, because we want to cancel out this radian and this radian. Okay, if you have RPM, can you we cannot cancel out the numerator and also denominator, radian and radian. Okay, because at the top part the numerator have radian, but the denominator only have round or revolutions, so you cannot cancel out each other. So now that, because of that, we need to first convert it to SI unit, which is the radian per seconds. Okay, remember, when you have round per minute, okay, if you tend to calculate everything involved round per minute, okay, make sure you need to do some conversions. Okay, so you cancel out radian and radian per second, so in this case you will get 1.3 seconds. The period, the unit for period is seconds, right? And this is angular acceleration. So what is angular acceleration? Okay, the same as our acceleration, our normal acceleration, or our linear. Okay, we can call it a linear acceleration, alpha. So this is alpha, not A. Okay, A is a linear acceleration, but right now is alpha. Alpha is angular acceleration. Now we have some terms: theta, omega, and alpha. Sorry, alpha. Okay, theta, omega, and alpha. So the average angular acceleration is the alpha average, that equivalent to delta omega over delta t. Okay, before this, when we talk about linear acceleration, so we will have something like this: delta v over delta t. Okay, so if you look carefully at the whatever happens in the angular part, it's quite similar to the linear part. It's very similar, but the one that give the different things is just the units, of course. Okay, the how you're gonna use the terms, which also different from the linear part. Okay, for example, in here we have alpha that equivalent to delta omega over delta t. If you look carefully, the units for average angular acceleration is equivalent to radian per second square. Remember, it have square, radian per second square. The time is square. Okay, so you can see that when you have theta, it will be radian. The unit is radian. Omega is the radian per second, and the alpha is radian per second square. Okay, it's also quite similar to the one that we have in linear, which is we have x meter, okay, v meter per second, and a meter per second square. Okay, now, okay, I have given some comparison between angular position, angular part, and also linear part. Okay, but we will discuss it later. Okay, what is the odds of the similarity between motion kinematics? Okay, all right. When angular velocity and angular acceleration have the same sign, angular speed increases. Okay, when angular velocity, this one is omega, and angular acceleration, this one is alpha. Okay, so the angular speed increases, but when angular velocity and angular acceleration have some opposite sign, the angular speed decreases. The same happens when we are in linear motion. Okay. Okay. Right. Look at the problems. Look at how it solved the problems. As the wind dies, a windmill that was rotating at 2.1 radian per second. Okay, the idea to solve the problems of involve angular whatever angular speed or angular position or maybe angular acceleration is you need to look at the units. Okay, the units will tell you a lot in order to for you to understand either this is theta, omega, or alpha. For example, okay, was rotating, look at the question, a windmill that was rotating at 2.1 radian per second. So this is going to be omega. Begins to slow with a constant angular acceleration. Constant angular acceleration of, okay, this one is alpha. How long does it take for the windmill to come to a complete stop? Okay, so now we have alpha. Alpha is equivalent to delta omega over delta t. What is delta omega? Omega final minus omega initial over delta t. Okay, because the questions wants you to find how long. How long we need to find delta t. Okay, so what is t? Now you need to get this alpha, this alpha to the denominator part, like this one. So bring down the alpha, right? So 0 means after we completely stop. So 0 minus 2.1 radian per second. Okay, we don't have to convert it to radian because the questions have already given you radian per second. It's not around per minute. Okay, so enough. So 2.1 radian per second, and then divide with the sum acceleration. Look at how they write down. Okay, it begins to slow down with a constant angular acceleration. That means, okay, the acceleration is decreasing. Okay, so you need to put the negative because the acceleration is decreasing until it stops the motions of the windmill. So this time we need to put a negative value to the alpha, and then with some with cancel from the denominator and also numerator, radian and radian, and second, just second, you bring out the second to the top part, and so you will get 4.7 seconds. Okay, how long does it take for the windmill to come to a complete stop? The answer is 4.7 seconds. Okay, this is another example taken from your textbook. Okay, taken from your textbook. The rotor on a helicopter, okay, that means the blade, on the helicopter turns at an angular speed of 320 revolutions per minute. 320 revolutions per minute. So this is omega, right? Sometimes we use the abbreviation RPM, but in most cases we refer as rev per minute. Okay, look at how they can write. Okay, maybe they can write it down as 3.2 times 10 power of 2 RPM, or maybe they can write down as rev per minute. Okay, the same happen, right? Revolutions per minute or count per minute, or they can also write it down as revolutions over minute. So express, right? Part A, express this angular speed in radians per second. So number one is they need us to get the angular speed or angular velocity in terms of radian per second, because this is the very good first step in for you to answer it, because in here they are only given you not an SI unit. So this is the very common things happen when you want to solve the problems involve angular. Okay, angular. When motions in angular, one thing for sure, they want you a little bit harder compared to motions. You need to convert it first to SI unit. So again, you need to memorize this one. Okay, theta is radian. Okay, omega is radian per second. Alpha is radian per second square. Okay, radian per second, or radian per second square. So if you are given revolutions per minute, it is not an SI unit. Okay, so therefore you need to convert it to radian per second. And again, okay, revolutions per minute. So one revolution is equivalent to 2 pi radian. You can cancel out one revolutions and a minute, and 1 minute equals to 60 seconds. So 3.2 times 10 power of 2 times 2 pi radian over 60 seconds. So the answer is 33.5 radian per second. And then look at part B. If the rotor has a radius of 2 meters, so this is R. What arc length does the tip of the blade trace out in 300 seconds? So this one is time. So that means what arc length does the tip of the blade, so you need to find what is the delta S, or what is S. S, you know, that is R equivalent to R delta theta. Okay, delta theta. So first you need to find what is the omega. Okay, what is the theta. Theta is equivalent to, okay, so theta is angular speed. So okay, first, obviously, where we have V equals to D over T, so theta omega is equivalent to theta over T. So theta is omega times T. Theta is omega times T, like this one. So now you have the theta omega times with the 300 seconds. So you will get delta theta, or you will get theta equivalent to 1.001 10 to the power of 4 radian. So that is the value of theta. But right now, the questions wants you to find the arc length. Okay, remember, this is theta, this is the arc length. So meaning that this is S, this is R. So S equals to R theta. Okay, R theta. So R is 2 meters times with this value. So you will get 2.02 10 power of 4 meters. 2.02 10 power of 4 meters. Okay, right. So let's look at the next part, which is the rotational kinematics. All right. So this is some analogies between the linear and rotational kinematics. For example, in the linear part, we have position. Okay, position, which is x, velocity, which is v, and we have acceleration, a. Okay, same happen when you have the angular quantity, because this is what we call angular position. This is what we call angular velocity, and this one is angular acceleration. Okay, so this is quite comparable to the one that we have on the linear part and also angular part. For example, position can be comparable. It's not equal. It can be comparable to theta, while v is comparable to omega, and a is comparable to alpha. So if you want to do some kinematics, for example, when we have a question like constant acceleration or constant angular acceleration, okay? So when you look at how they write down the equations down here, okay? So basically, this is the linear equations. And look at the left part first, which is v equals to v naught plus at, okay? Because the terms or the correct conditions when you can use the equations of linear equations like 2.7, 2.10, 2.11, and 2.12 here is based on when acceleration is constant. Okay, this is the rules that allow us to use a linear equations. Okay, so now we have v equals to v naught plus at, x equals to x naught plus half v naught plus vt plus v times t. Okay, now you also have x naught plus v naught t plus half at squared. Or also you can use a v square equals to v naught square plus 2a delta x. So this is delta x, okay? And of course, we also can use it in y-axis. Okay, but in the angular equations, everything that you write down in the linear equations can be comparables to, because x is comparable to theta. So in this case, we can also write it down in terms of angular equations. Why? Because there must be some rules that allow alpha to be constant. What is alpha? Alpha is angular acceleration. So therefore, we can also write the angular equations based on the or mirror to the linear equations. Not you don't have to use the same value, but if you look carefully, 2.7 is quite mirror to 10a, which means we have when we have v equals to v naught plus at, we also have omega equals to omega naught plus alpha t. Everything is changing from v to omega, or v naught to omega naught, and alpha a becomes alpha. What is the the one that doesn't change from linear to angular is just t, time. You look carefully, this one have time, this one is also time. Everything when it involves time, it doesn't apply. Okay, it can just stay whatever it has for the time. Okay, in the linear equation they have time, angular equation also have time. Everything, okay, every possible terms, x becomes theta, v becomes omega, a becomes alpha. So now you may have see that this is where you can play around with the angular kinematics. Okay, When you right now you have studied about angular quantity. So right now you can write down some angular equations. And of course, when we talk about angular quantity and angular equations, there must be some problems, okay, occur. Okay, for example, this question: to throw a curved ball, a pitcher. Okay, this is the pitcher, pitcher, pembaling dalam baseball, we call that as a pitcher. Give the ball an initial angular speed. Look at how they write down. Okay, initial angular speed. This one is omega naught at 36 radian per second. And 36 radian per second is already in SI unit. Okay, when the catcher glove the ball 0.95 5 seconds later, so this is T, its angular speed has decreased. Its angular speed has decreased due to a resistance 2. This one is omega F. What is the ball angular acceleration, assuming it to be constant? Okay, so the words and constant acceleration here. Okay, that means this is constant acceleration. Okay, when you look at the question that have constant acceleration, yes, you need to use some linear equation, some equation. Okay, so in this case, we're gonna learn about, we're gonna use angular equation. What is angular equation? Okay, right now we have omega naught, we have time. So what's left is we need to find alpha. Okay, the alpha is given by, so you can use this equation. Omega equals to omega naught plus alpha t. Okay, so omega minus omega naught divided by t is equivalent to alpha. Right? So what is omega? Omega is 34.2. The omega naught is 36. Okay, divide with time 0.595. So you will get some negative value of alpha. So you need to put the negative, because it means the ball is slowing down. Okay, the ball is slowing down, okay, at negative 3.03 radian per second squared. Look at how they write the equations and the unit, radian per second squared. So the keywords or the key things in order to learn this topic, excellent. So you need to memorize the unit of each angular part. Right. So the next question is how many revolutions? How many revolutions? Okay. How many revolutions? Look at how they write the questions. So meaning that they want to find theta. But theta is in radian. So when you have a radian, when you solve the problems afterwards, you will get radian. So then you need to convert it back to revolutions. So look at how they respond to the questions. So we can use a lot of equation here, a lot of equations you can use, but try to get the best one suits the problems. Okay, now we have theta equals to theta minus theta naught equivalent to omega t, omega naught t plus half alpha t squared. So from here you can get 20.9 radian. Okay, but the question asks you about how many revolutions. So you need to convert from radian to revolutions. Again, 20.9 radian. Okay, you can convert it to revolutions. The answer is 3.33 revolutions. So that is your last answers. Except for this one. Okay. All right. So look at the next examples. On a certain game show, contestants spin a wheel when it is their turn. One contestant gives the wheel an initial angular speed of 3.4 radian per second. This one is omega. Okay. One contestant gives the wheel an initial angular speed. This one is omega naught. It then rotates through 1 1/4 revolution. 1 1/4. 1 1/4 revolutions. So this one is some sort like theta and comes to rest on the bankrupt space. So it's like a wheel of fortune. Okay, it returns, it'll have some initial velocity, the initial angular velocity, and then after 1 1/4 revolutions, so this will stop at the bankrupt space. Okay, at here. Okay, it will stop here after 1 1/4 revolutions. Okay, so this is not the correct way to write the theta. So you need to measure theta 1 1/4 of revolutions to radian first. Okay, in order to solve the problems, this one is already, you got the omega f is considered to be 0. Okay, so we need to use some equations, the correct equations that possible. If you look carefully inside, the question doesn't involve any time. So because it doesn't involve any time, definitely we're going to use omega square equals to omega naught square plus 2 alpha delta x. Okay, so right now you you need to measure what is the here alpha. Okay, what is the alpha first, right? From here, for example, now we're going to use this kind of equations. Omega equals to omega naught plus 2 alpha delta theta. Okay, sorry, this one should be delta theta. Sorry, okay, this one should be delta theta, not delta x. Okay, so delta theta. So alpha is omega square minus omega naught square divided by 2 alpha theta, delta theta. So the delta theta here, okay, now we have one equations. Okay, we have one equations. Another one is from the delta theta itself. So delta theta is 7.85 radian, calculated from this one. This one is considered to be 1/2 revolutions. So we convert it to 1.25 revolutions, but we need to convert it to radian because revolution is not the SI unit for theta. Okay, the answer is 7.85. Then from here we can get alpha the equivalent to negative 0.736 radian per second square. Okay, all right. And how long does it take for the wheel to come to rest? Okay, berapa banyak masa diperlukan untuk wheel ini berhenti? Okay, then we can use this equation back. Omega equals to omega plus alpha t. So you need to find what is the t. The answer is 4.62 seconds. Okay, you can use the equation 0, for example, because it should be, it should stop. Okay, because the spin will stop at some place, which is at the bankrupt space. Okay, and then this one is the omega naught, this is omega final, and this one is as a acceleration. Lastly, you can get time that is equivalent to 4.62 seconds. Okay, a pulley rotating in the counterclockwise direction is attached to a mass suspended from string. Okay, the mass causes the pulley angular velocity to decrease with a constant acceleration. Okay, to decrease. Okay, if the pulley's initial angular velocity, so that means the mass causes the pulley angular velocity to decrease with the constant angular acceleration. This one is alpha. This one is omega naught. Okay. If the question is only given the value of omega naught only given in the part A. Okay. How long does it take for the pulley to come to rest? Okay. How long for the pulley to get it to come to rest? That means, okay, at part A, we have note that omega final is equivalent to 0. Okay, and from here, we can replace the alpha with the negative 2.1 radian per second square. So the answer is T equivalent to 2.57 seconds. Okay, now we can rearrange this equation to become T equivalent to the omega minus omega naught over alpha. Okay, and omega is 0, omega naught is negative, omega naught is 5.4, so negative cancel out with the negative omega, which is 2.1 radian per second square, and then what's left is the second, 2.557 seconds. The next question is, through what angle? Through what angle? That means they want to find theta. Okay, does the pulley turn during this time? Does the pulley turn during this time? So you need to calculate the theta based on the answers. From T, you have T equivalent to 2.57. You have omega naught that is equivalent to 5.4 radian per second. Okay, alpha. Okay, alpha is negative 2.1 radian per second square. Okay, and then you will get the answers at 6.94 radian. Okay, the answers for part B doesn't show any indicator of what type of rate or theta that they want to calculate. It's either revolutions or round or maybe in radian. So you just the safest way to answer the problem is just put it in SI unit. Okay, the SI unit is radian. So just leave the answers in radian. Okay. So a wheel rotates with a constant angular acceleration, and this one's taken from your textbook. Constant angular acceleration, this one is alpha. If the angular speed of the wheel is 2.2 radian per second, this one is omega naught. Okay, because at t equals to 0, through what angle does the wheel rotate between t equals to 0 and t equals to 2 seconds? Through what angle? So they want to find the theta, right? So in here we get delta theta equivalent to, from this equation, using this equation. Now you have alpha, you have omega naught, so you have time, so you can calculate the delta theta. Give your answer in radians and in revolutions. Okay, this is one is radian. In revolution is here, 1.75 revolutions. Right. What is the angular speed of the wheel at time t equals to 2 seconds? What is the angular speed? What is angular speed of the wheel at time t equals to 2 seconds? So then you need to use some equations. Not just do a normal equations, but right now use the correct terms, which is angular. 2 radian per second plus with 3.5 radian per second squared times 2 seconds. So you will get 9 radian per second. Okay. And the last question is, what angular displacement? And the question asks you to get it in revolutions. Okay, in revolutions. So that means you need to find what is theta first in radian and then convert it to revolutions. Okay, right? So in here we have while the angular speed found in part B doubles. Part B, so the value of part B, now you need to double up the value. So the angular angular speed found in part B is the angular speed at time t equals to 2. So you need to use time t equals to 2. But right now, the double the answers in part B. It doubles the value. So that means here you can see the value have been doubled for the final position, final velocity. It becomes 18 radian per second square. Sorry, 18 radian per second. That value is square because this equation, omega final square minus omega initial square, okay, this actually comes from this equation. Omega square equals to omega naught square plus with 2 alpha delta theta. 2 alpha delta theta. So this is the equation now have been converted to this part. Okay, So in the end, the answers for delta theta is 34.7 radian. And then the answer asks you to find in revolutions. So you will get to 5.52 revolutions. Okay, so I think we will stop here. Okay, and we will continue our lecture again. So do you have any questions? Ada soalan? Okay, so let's continue our lesson. Let me share the slide. Okay, so let's do some recap. Okay, right now we are already in chapter 6. Okay, sorry, chapter 7, the rotational kinematics and energy. So in the chapter 7, we will learn about angular positions, velocity, and accelerations. And with the constant acceleration, we also going to learn about rotational kinematics, which involve the equations of angular. Alright, so as usual, the angular position is theta. Okay, angular velocity is omega, and angular acceleration is alpha. Okay, and one revolution is also known as one circle, one round is equivalent to 360 degree, and in radian is called 2 pi. Right, okay. So the arc length is the panjang lengkup. Arc length is measured in radians. S equals to r theta, in which r is the radius, while theta is the angular position. Okay, what is angular position? Angle in terms of position in terms of angle. Okay, so this is angular velocity. It also use the same method as what we learned in kinematics. Okay, if we have in the kinematics we have average velocity, in the rotational kinematics we will also going to learn average angular velocity. Okay, just that angular velocity is based on theta over time. Okay, and for as usual, time is independent here because time it cannot be deferred to other forms. Okay, but in terms of position, in terms of velocity, and also acceleration, okay, everything is based on angle. All right, so the unit for position, angular position, is radian, while the unit for angular velocity is the radian per second. All right, and these are the sum of the examples. Okay, and through the conversation or through the some equations involve positions and also omega. Okay, we can derive one equations that is equivalent to period. Okay, the period is not time. Okay, but the period is the quantity of time, which means the period is the one complete time taken for one complete cycle. Okay, one period is one complete cycle. One time taken for one complete cycles. So we can get 2 pi over omega. Right? So this is angular acceleration. Same situation as the in linear we have acceleration. Okay, just add the word angular. Okay, right? So the unit for angular acceleration is radian per second square. Okay, radian per second square. And of course, when it involved in one particular situations, okay, everything is it must involve from theta, omega, or alpha. Okay, theta, omega, theta, omega, or alpha. Okay, these are some examples. And these are the rotational kinematics. Basically, when we talk about rotational kinematics, it involves some equations. But in order for us to use this equation, we must make sure that the alpha is constant. Okay, alpha, which means our angular acceleration is constant. Same situation as in linear. While if we want to use the linear equations, okay, we must make sure that the situation is based on a constant acceleration. Okay, constant acceleration. Okay, bear in mind. And of course, when you look at the similarities between the linear and angular, okay, it can be comparable to each other. Okay, for example, in linear quantity we have x as the position. In angular quantity we have theta as angular position. For the velocity in linear quantity we have v, but in the angular quantity we have omega. This is omega. Okay, and for the acceleration we have a, and for the angular quantity we have alpha. Okay, x comparable to, it's not equal, it's comparable to x comparable to theta, v is comparable to omega, while a is comparable to alpha. Okay, when we try to look at the bigger picture, okay, we can use it in terms of equations. Yes, if you look carefully, v equals to v naught plus at, okay, equal in linear equations. So if you try to make it into angular equations, it becomes omega equals to omega naught plus alpha t. Okay, everything must be comparable to the one that we did just now. Okay, v is equivalent to v is compared to omega. Okay, so you must replace v with the omega. You can replace v naught with the omega naught, and you can replace alpha a with the alpha, but not time. Time is independent, of course. Okay, and every situations involving linear equations such as velocity, okay, we have alpha a, we have x, and we have position. Everything can be comparable to angular equations, and we can replace that. In linear equation, we can replace all the linear equations symbol such as x, v, a. Okay, we can replace with the theta, omega, and also alpha. Okay, these are some examples, okay, involving problems with the angular equations. Okay. Okay. Right. So these are also some examples. Okay, we have already done all the examples here. And lastly, for the last subtopic for today, at least for this chapter, okay, is the connections between linear and rotational quantities. Okay, so before this, okay, when we talk about, let's say we talk about x or y, it can be comparable to theta. Okay, while v can be comparable to omega, and a can be comparable to alpha. Okay, it says here, okay, if you want to use some equations, for example, for instance, we have let's say, okay, so let's say if you try to get v first. Okay, now we will talk about v. Okay, so it says here that the tangential speed. Okay, what is tangential speed? If you look carefully at the merry-go-round situations, this is some some boys, okay, riding a horse at the fun fair. So this horse is basically um, have some radius towards the center. Okay, if you look carefully, this some radius towards the center, and if you look carefully, this horse is actually static at one place. Okay, it doesn't move around because this is not a real horse. Okay, and when the machines work, okay, the horse will bounce up and down and try to move around. uh, in our terms, okay, the horse is actually having a rotational motions. Okay, so when the horse is actually try to ride to the front, okay, try to move forward, try to move forward, so we are saying that this horse is actually having some tangential speed. Okay, this is what we call tangential speed, vt, the tangential speed, that is equivalent to r omega. Okay, so we can note it here that if you want to discuss about, or if you want to see some connection between linear and rotational, so we take place between v and omega first. Okay, because it's obviously, if you want to make or if you want to relate a linear equation, which is v, speed. Okay, this in this term is speed, and omega, the angular speed. So we just put r in the front of the omega. So the equation will become v equivalent to r omega. And the unit for this one is basically based on v, which is meter per second. Okay, so if you try to calculate v equals to r omega, then the unit must be in meter per second. Okay, it is also known as tangential speed. That means the speed that is tangent. Okay, why tangent? Because if you look carefully, this speed is actually 90 degrees to the radius. Okay, the speed is actually 90 degrees to the radius. And this is the radius, and this is the center of the circle. So therefore, we can say that this is a tangential speed. Okay, so if try to make it a bit in depth in terms of because we before this we learned about a centripetal force. Okay, for those who can't remember centripetal force is based on the uh, Newton's second law, which is FCP. The centripetal force is based on mass times with the centripetal acceleration. So what is centripetal acceleration? Okay, centripetal acceleration is equivalent to v square over r. Okay, v square over r, velocity square over radius. Okay, velocity square over radius. So the true is mv square over r as a FCP. Okay, but in terms of this is in terms of velocity, but if you want to make it in terms of angular speed, okay, so what happened to the centripetal force? So let's say you have FCP equivalent to mv square over r, and noted here, okay, noted here that v is equivalent to r omega. Okay, what happens if you try to replace v with the r omega? So right now, m r omega squared over r. So what happened is m r square omega square over r. So you can cancel out one r. So it becomes FCP can be also noted as mr omega squared. Mr omega squared. Okay, that is for a centripetal acceleration. So centripetal, in the words, centripetal acceleration can be noted as r omega squared. Means, except before this, if you have velocity, so or speed, we can use this equation v square over r. But in terms of omega, okay, in terms of omega, the centripetal acceleration can also be known as r omega squared. R omega squared. So that is depending on the situation. If the question doesn't give you omega, okay, then you need to use v. And right now you already know that velocity can be converted to omega, and omega can be converted to v by the equations v equivalent to r omega. This is the some these are the connection between linear velocities and also angular velocity. And the unit for centripetal acceleration is still meter per second square because it is a meter, it is a acceleration. Okay, so don't forget about when we interpolate the centripetal acceleration. So the force, the centripetal force can be also known as mr omega squared. Just add m to the equations. Okay, r omega squared, okay, times with m, so you get mr omega squared. This is not w again, this is not w, this is omega. Okay, but I often use it as I often write down as w, but it is a omega. Okay, let's look at the situations here, right? In a micro hematocrit centrifuge, a small samples of blood. Okay, so you should know that the centrifuge is actually, if you want to um, the blood, okay, if you want to make the blood, okay, go around with some a very high or very uh, speed, okay, like 11,500 revolutions per minute, okay, a very um, high speed at in 1 minute, with the bottoms are placed in the heparinized capillary tubes. Okay, the tubes are rotated at 11,500 RPM. Okay, so what is RPM? Revolutions per minute. So you know that when you talk about revolutions per minute, we know this one is the omega. Okay, with the bottoms of the tube is 9.07 centimeters from the axis of rotation. So that means this one is R. Find the linear speed of the bottom of the tube. Find the linear speed. So V equals to R omega. But first, you need to know that in order for us to understand and to make it a very clear situations, we must make sure first to convert from RPM to radius per second. So you need to convert it to radius per second. So that's why the first step is you need to convert the 11,500 revolutions per minute and convert it to radian per second. So again, revolutions per minute, 2 pi radian is equivalent to 1 over 1 revolutions. So you can cancel out 1 revolutions, and 1 minute equals to 60 seconds, and then 11,000 times 2 pi radian over 60 seconds, you will get 1,200 radian per second. Okay, and about 1,200 radian per second. And then you can put that value in the equations. V equals to R omega. Okay, R is, okay, you make sure that R is in SI unit also, because here is centimeters, so you need to convert it to meter. Okay, and then the meter is 0.0907 meters. Okay, times is with 1,200 radian per second. So the answer is 109 meter per second. Look at how the units used is all in SI units. Okay, and part B, what is the centripetal acceleration at the bottom of the tube? Centripetal acceleration. So there are two ways to measure the centripetal acceleration. For instance, we have ACP equivalent to V square over R, or ACP equivalent to R omega square. It depends on you. Okay, depends on the situation. In fact, in these examples, okay, they provided us with two possible situation or two possible answers that give you the equal value. Okay, for instance, okay, number one is they are using R omega squared. So after replace with the R a 0.0907, and then replace with the omega with the square, and they will get 1,031 131,000 meter per second square. While at the same time, if they are using the linear velocity, the linear speed again, or linear speed square over r, v square over r, so they can also get 131,000 meter per second square. So we will get the same value if you use the correct manner, or we use the correct units. So in this case, the important part is of the question is you need to know that all calculations involved must be in SI units. Okay, must be in SI units in order to get the correct value. Okay, so let's go to the part of the acceleration. So where is actually tangential acceleration and centripetal acceleration? So in here, okay, if try to make, if you look at one particular point that go around or move in the rotational motions towards some O is called center, center. So this is a center of the circles, and one object move around with some acceleration, with some velocity and acceleration. Okay, so because of the ball, or you can say this is the ball, one ball, okay, try to move around that circles, so that ball will have some centripetal acceleration. Yes, okay, because before this, we have learned that the centripetal acceleration is the force, is the acceleration that have a directions towards the center, towards the center of rotation. Okay, you should know that the centripetal acceleration is a acceleration that, okay, acts towards the center of the rotation. Okay, meaning that these are the directions of the centripetal acceleration. Okay, the centripetal acceleration is acts towards the center. It's always towards the center. If you put it here, okay, it's also pointing towards the center. Okay, if you put it here, for instance, if the ball is here, it's still towards the center. The ACP is still towards the center. Okay, and then because of that, okay, we managed to see the tangential acceleration. So where is the tangential acceleration? Look at the word tangential acceleration. Tangent is tangent of the acceleration. That means if you move in circle, if you move in the some circular motions, so the drive that move that around, okay, the move the ball around is based on the tangential acceleration. Okay, why you can make this ball move uh, around the circle is because of the centripetal acceleration. Of course, based on centripetal acceleration, and of course it leads to the centripetal force. But what drive around, make sure that the ball still move with a certain speed and also acceleration is based on tangential acceleration. So what is tangential acceleration? Is the tangent. Okay, you look at the radius, and where is the tangent? Then there is some tangential acceleration. So it's noted here that the tangential acceleration is actually r alpha. R alpha. So I would like to remind back that our VT, or the tangential velocity, is based on r omega. Okay, but for tangential acceleration, the equation is r alpha. Okay, the equation is r alpha. You look at here is r radius times alpha. So what is alpha? Our angular acceleration. And the unit for tangential acceleration is meter per second square. Okay, so try to make it. So what is the difference between tangential versus the centripetal acceleration? Okay, so the tangential acceleration is due to the changing of the angular speed. Okay, tangential acceleration is due to the changing of omega final minus omega initial. while at the same time, the centripetal acceleration is due to the changing of the directions of motion because it doesn't influence by the situation. Because if you look carefully, ACP is just r omega squared. But in terms of r alpha for the tangential acceleration, alpha is due to omega f minus omega I divided by t. So that's why it is due to the changing of angular speed. But for the centripetal force, it doesn't change much because it just involves r omega squared. It's just in terms of motion. The positions of angular position is changing, and then of course it just changed the motion because every time the centripetal force, centripetal acceleration, okay, as I'm saying just now, okay, it will act towards the center. Okay, so that's why we can say that, look carefully, all right? So these are the centripetal acceleration, okay, pointing towards the center, and the tangential acceleration is pointing away, it's actually pointing forward, which is 90 degrees to the centripetal acceleration. So A, tangential, and centripetal acceleration is 90 degrees to each other. Okay, so you need to know, and of course, when we try to combine both equations, so we can get the total acceleration. So sometimes this is what we call as total acceleration. So what is total acceleration? AT square plus ACP square. So that will give you some total magnitude of acceleration. Okay, and then of course you can see that when we have ACP, this one is phi is equivalent to tangent -1, okay, centripetal acceleration over tangential acceleration, then will give you some value. That value is based on this part, okay. These are the angle phi. Okay, angle phi. Sorry, this one is not the angle phi here. Okay, the angle should be here. Okay, the angle should be, sorry, this one is not theta, it should be phi. The angle between the tangential acceleration and also centripetal, and also the total magnitude of acceleration. Okay, so this merry-go-round has both tangential and centripetal acceleration. So have, okay, these are the angle. So you can see here, okay, the horse is moving forward, but at the same time, the horse is oblique to the one that, because of the block, the horse is not the real horse, and but it's still moving around the merry-go-round. But so because of that, we can say that the object in the situations of a rotational motion will have a centripetal acceleration, which the acceleration is towards the center, and we also have the tangential acceleration, which drive these things around. Okay, if it doesn't have a tangential acceleration, of course the horse is not moving. Okay, so that's why we can say that in both when object move in the circular, okay, sometimes, okay, or most of the times, okay, it will be oblique to some centripetal acceleration, and at the same time it will have a tangential accelerations. Okay, so look at some examples here. Suppose the centrifuge in example 10.3 is starting with a constant angular acceleration. So this should be your alpha. Okay, what are the magnitudes of the centripetal, tangential, and total accelerations of the bottom of the tube when the angular speed is 8 radian per second? So this one should be omega. So you need first to calculate the omega you need to calculate the alpha based on omega. But here, okay, we can get first the total centripetal. What are the magnitudes of centripetal acceleration? So ACP is based on r omega squared. So you can use this omega radian times with the omega squared times with r, okay, times with r. So you will get the value, right? So the one that this one is taken is also taken from the one that we did that just now. The r is 0.0907 meters times with your omega, and then you will get 5.8 meter per second square. Okay, and how about tangential acceleration? So tangential acceleration is r alpha. So after you get the alpha, okay, because alpha is 95 radian per second square, you times with the 0.0907 meters. So you will get 8.62 meter per second square. And of course, this one is the total acceleration, which is equivalent to 10.4. Use the sum equation, and you can get the phi that equivalent to 33.9 degree. Okay, 33.9 degrees. So all is happening here. Okay, which is this one is a tangential acceleration, centripetal acceleration, and the total acceleration. Okay, so normally we will talk a lot in terms of centripetal or tangential accelerations. Okay, so look at another examples. Apply a compact disc rotates from rest up to an angular speed. So this one is omega naught 0. This one is omega in time. So this one is t. What is the angular acceleration? Assuming the angular acceleration is uniform. So alpha equivalent to omega minus omega naught of t. So 31.4. Okay, the units for omega is already in radian per second, so you don't have to measure it. You don't have to convert it, and 0.892 seconds. So you will get 35.2 radian per second square. Okay, through what angle does the disc turn while coming up to speed? Through what angle? So through what angle, that means they want to find position. Okay, so position. So meaning that they want to use, they want to see what is the angular positions when it change. Okay, okay, when coming to a speed. So you can measure it with the value. Then omega naught initial is 0, so the only left is half alpha t square. So you can put that this value in this alpha. So you will get 14 radian. Okay, and then part C is if the radius of the disc is 4.4, so this one is R. Okay, this one is R, but you need to change to meter. Find the tangential speed of the micro rope riding on the rim of the disc when t equals to 0.892. So again, the tangential speed R omega. So use R omega. So R is 0.04. You need to convert it to meters, and then you can times with the 31.4 radian per second. The answer is 1.4 meter per second square. Look at all the units used. Okay, don't bother much about you can look at the how they did, but also look at the units, because sometimes they will use radian per second, sometimes it change to meter per second. Why? Because that's depending on the situation. The question asks you about the tangential speed, okay, not the angular speed. Right. So part D, what is the magnitude of the tangential accelerations? So again, you will use that alpha A equals to R alpha. So R, and you put that value of alpha. So you will get 1.57 10 power of 1.57 meter per second square. Okay. So this also the last example, I think, right? In a compact disc player, as the reed head move out from the center of the disc, the angular speed of the disc change so that the linear speed and position of the head remains as a constant value. So speed V have 1.3 meter per second. Okay, 1.3 meter per second. Find A, the angular speed of the disc when the reed head is r equals to 2 centimeter, and again at r equals to 5. There are two possible situation, which is at r equals to 2 and also r equals to 5.6. Alright. So at first you need to know that the meter per second is V, the tangential speed. So you need to convert it to omega in order to calculate the other angular speeds. Okay. Alright. So you use that value. So 1.3 would V equals to R omega. So omega is V over R. Okay, so V is 1.3, R is you have 2, which is 2 centimeters, and also 5.6 centimeters. So you will get omega, a certain omega as 65 radian per second, and also 23 radian per second. Okay. And part B, an old-fashioned record player rotates at an constant angular speed. Okay, what is the meaning of constant angular speed? We are saying that alpha will be 0. Okay, but look at the situations. Okay, constant angular speed alpha 0. So the linear speed of the record groove moving under the detector changes. Find the linear speed of 45 RPM record at points 2 and 5.6 centimeters from the center. So that should be your R. Okay, so in order to do that, you need to convert it first to radian per second, because now we have RPM. Again, 45 RPM, revolutions per minute. You need to convert it to radian per second. So first we need to convert it, and then of course the question asks you about the linear speed. Okay, the linear speed V equals to R O omega. So first we can use that this is the value of omega from part A. Okay, from part A. Okay, 4.71, which is the value of omega here is based on omega calculated. Sorry, not from part A, but calculated from the question itself, which is 45 RPM. So you can use this value and use this value based on their own or respective radius. Okay, 4.71 times with its own radius at 2 and also at 5.6. Okay, and in part C, in both the CDs and phonograph record, calculate the total length of the track for a CD designed to play for 1 hour. Okay, calculate the total length of the track for a CD designed to play for 1 hour. Okay, 1 hour is equivalent to 3,600 seconds, because 1 minute is 60 seconds and 1 hour is 60 minutes. Okay, 60 minutes times 60 seconds, so you will get 3,600 seconds. Okay, so times with V, because V is equivalent to a distance over D. We want to find what is the distance. So D equals to V times T. So that V is 1.3 based on our given values. Okay, 1.3, and of course times with the C. Okay, times with the T, 3,600. Okay, 3,600. So you will get 4,700 meters. Okay, of the total length of the track for CD designed to play for 1 hour. Okay, all right. Okay, so these are some, we should recap the summary of the chapter 7. Okay, so when we try to discuss about rotational or angular position, we talk about omega theta. Okay, and we're going to talk about omega, which is angular velocities, and we talk about alpha as angular acceleration. Okay, the period is equivalent to T equivalent to 2 pi over omega. T 2 pi over omega. And then we learn about the comparable of linear and also angular quantity together with the linear and angular equations. And lastly, about tangential, centripetal, and tangential acceleration. Okay, tangential speed, tangential acceleration, and also centripetal acceleration. Okay, so let's take a break for a while, and we will continue on the next topic. Okay, so let's continue on the next topic. Let me share the slide. Okay, so the next topic will be rotational dynamics. Okay, the rotational dynamics. Okay, before this, we learn about rotational kinematics. That means motion. Okay, but in everything that move in rotation, which is the circular. Okay, circular motion. All right. So right now we want to learn about rotational, but in terms of dynamics. So what is dynamics? Okay. So in the dynamics, we will learn about the torque. Okay, torque and the two conditions of the equilibrium. Okay. The center of gravity, we just briefly touch about center of gravity, and also the objects in equilibrium, and lastly the relationship between torque and angular acceleration, and last but not least the angular momentum. Okay, so let's look what is torque. Okay, if you look carefully, before this, okay, we learn about rotational motion. Okay, rotational motion, rotational kinematics. Okay, the rotational kinematics or motion in circular, motion pergerakan di dalam bulatan. Okay, but that is based on motion. So when we talk before this, okay, in the real life, when we talk about kinematics, when we learn about motion, okay, we will discuss a lot what is acceleration, what is velocity, and what is the position. Okay, and of course, we're gonna see what to use inside the linear equations or angular equations. But further after that, okay, because of now it involves the circular, the rotational have already established in terms of motion. So right now it move a little bit further in terms of first the torque. So what is actually torques? Okay, so try to imagine this. Okay, it's very good to imagine when you try to move or when you try to go around some revolving doors. This is what we call revolving doors. Okay, pintu yang boleh berpusing ni, revolving doors. Okay, so that actually we have one man pushing the revolving doors, but quite near to the center of the rotation. So this is called center of rotations. And you have one child, okay, that push the door at the very end of the doors actually, okay, slightly away from the center of the rotations. Okay, so this is what happens when you look at this. We logically, this man, okay, this man should have more power, should have more force to push the door, to make the door revolve. Okay, but at the same time, you can see that this girl, which is much more small compared to the man, okay, can easily push the door in order to make it rotate. Okay, so try to imagine that. That means this man and also the girl is applying some force. Okay, the girl is applying F1 while the man is applying F2. But the main different thing between the man and the girl is just the distance that they applying the force. Okay, the distance in this case, the distance from the center of the rotation. Okay, the distance from the center of the rotations will give some different value between the man and the girl. If the girl try to move towards the center of the rotations, what will happen? Is she gonna have some trouble to make the door rotate? Yes or no? So we will see what will happen to her. and to the man. Okay, so from experience, we know that some force will be much more effective at rotating an object. Okay, force will be useful in rotating an object. For example, in the revolving doors, and also as when you are using a wrench like this. This is a wrench, and also the nut. Okay, and also to tighten the screw, and to tighten the nuts, okay, you need to use some wrench. Okay, so which side, okay, which is good to the good place to place your hand to tighten the nuts? Is it F1 or F2? So it will remains it will be answered from this chapter. Okay, so this is actually based on the rotational force. Okay, the torque can be referred to rotational force. Okay, actually we are applying some force in the rotational motion, applying a force to rotational motion. Before this, we apply velocity, but in rotational it becomes omega. When we apply some acceleration to the rotational, it becomes alpha. When we apply some position to the angular part, it becomes theta. So when you apply a force to the rotational, so it becomes torque. And then the torque is defined as Rf. Okay, Rf, in which we are saying that the SI unit for torque is Newton meters. Okay, and R is not exactly a radius. Okay, we cannot say that R is the radius. R is the what we call that, lever arm. Okay, lever arm. Okay, so now you can see before after this, what is the lever arm? All right, and F is what we call as force, and this tau, the symbol is known as tau. Okay, but this one is called torque. T-O-R-Q-U-E, torque. The SI unit for torque is Newton meters. Okay, so R is lever arm and F is force. Okay, and remember R is not obviously radius. Okay, because for example, in this case, okay, obviously the revolving doors is can make a rotation, okay, a circle, but if you look at the first example, which is the wrench and the nut, okay, it doesn't show much about rotation, but you can see it's a parts of the rotations, parts of the big circle. Okay, parts of the big circles. Okay, it's still part of the big circle, so we can say that it's also a rotation. Okay, but that's why we are saying that there's some lever arm. Okay, so try to imagine these things. Okay, because when you look, the torque increases. Okay, the torque increases as the force increases. Okay, and also the distance increases. Okay, so everything looks okay. The torque is actually directly proportional to force and distance. But which type of force? Okay, the one that should be considered increase. Okay, when we have only component of force. Okay, component of force that tangent to the level R. Okay, component of force that tangent to the R. Okay, so let's look at the situation here. Okay, so what is component of force that tangent to the R? Okay, let's look at one particular situation. Okay, this is one boy and his siblings or brothers. Okay, he tried to push, okay, some in the some mini, this is like a mini merry-go-round. Okay, mini merry-go-round. So he tried to push this revolving mini merry-go-round, but he tried to use two ways. Okay, number one is he tried to pull. First, he tried to pull, which is here, for his force and the lever arm is actually parallel. The theta is 0 here. Here is the theta is 0, and afterwards he tried to make sure that what happened when the theta is 90 between the lever arm and also force. Okay, slightly have a theta. Okay, not just theta 90, but from theta from 0 to 90. Yeah, from 0 to 90 degrees. So in this case, he will get 0 torque when theta is 0, and he will get the torque when there is some angle and there is some theta. Okay, so which component of force that we are applying now in order to get force? So this should be the one that you should know. Before this, the torque is equivalent about RF. Okay, RF meaning that lever arm times with the force. So the correct way to understand the torque is torque based on R times with F sine theta. Why F sine theta? Okay, if you look carefully at the situation here, okay, look carefully, the theta is the angle between the lever arm and also the force. Okay, the lever arm and also the force, which is here. So right now we have force over here. Okay, so the component of force, because of the angle, it become, so here we have F cos theta, and in this part we have F sine theta. Okay, we have F cos theta and F sine theta. So when you put that value, okay, you give that value, let's say the theta 90 or any kind of number theta, except 0, okay, because if you look carefully, we have two components. We have component of that parallel to the R, and also we have component that perpendicular to the R. Okay, so the one that we should consider in order to calculate torque is the component of force that perpendicular. Okay, component of force that perpendicular to the lever arm. So that's why these general definitions of torque. Okay, so R lever arm times with the component of force. Remember, component of force that perpendicular to lever arm. Okay, sometimes they call it radius, sometimes they call it lever arm. Doesn't matter, but it's just radius, or it's just distance from the center of the rotations to the force. So that is why we call lever arm. Okay, if you like, try to look carefully. Okay, this, if there's some circle over here, this one is your R. Okay, and this one is your force, and of course the theta is between the force and also the lever arm. Between the force and also lever arm, and you can measure this one. You will have F cos theta, and you will have this one is F sine theta. That the one that we consider is F sine theta times R. So that's why you will get, okay, torque is equivalent to R F sine theta, where the theta is the angle between the lever arm and also force. Okay, these are the good examples. Okay, if the torque causes a counterclockwise angular acceleration, it should give you positive value, while if the if the angular acceleration clockwise, then it becomes negative. Same happens when we discussing about uh, the acceleration when you have a clockwise acceleration, so it becomes positive negative. When we have a counterclockwise acceleration, it becomes negative. Okay, so try to imagine these things and then we try to look at the situations. Okay, these are some examples. Two helmsmen in the disagreement about which way to turn a ship. Okay, basically, this is the steering of the ship. Exerts the force shown below on ship's wheel. The wheel has a radius of, okay, this one they call it radius because the wheel is actually have a perfect circle. Okay, 0.74 meters, and then the two forces have the magnitude F1 72 Newton and F2 58 Newton. Okay, this one is 58 Newton and this one is 72 Newton. Find A, the torque caused by F1, and B, the torque caused by F2. Okay, F1 and F2. Okay, right. So torque number 1, now we calculated torque number 1 first. Okay, the angle between the torque is 50. The angle between torque and the force is 50. So therefore, you can use this equation. Torque equals to R F sine theta. So R is 0.74 in meters. Okay. Okay, we should agree that all values should be in SI unit. Okay. And F is the 72 Newton sine 50. Okay, why sine 50? Because, okay, you look carefully. Yeah? This one is 50 is here. Okay, so this one is F1 cos 50. And the one that here is F1 sine 50. Okay, the one that we should consider is the one that the component of force that perpendicular to the lever arm. Okay, one that perpendicular to the lever arm, right? So RF sine theta, F1 sine theta, so sine 50, 0.74, 72 sine 50, you will get 41 Newton meters. Okay, 41 Newton meters. Okay, look at the torque number 2, which consider to the force number 2. Okay, force number 2, it actually the 90 degrees. Okay, 90 degrees. Okay, so torque number 2 is RF2 sine 90. Okay, sine 90 because it's already in perpendicular to the lever arm. Okay, perpendicular to the radius. But why we put negative value? Okay, so basically, this force number 2 will make the wheel turns to the clockwise position. Okay, so because of that, we should put it negative because this is in clockwise. While if you look carefully, if you think logically, that F1, when you try to push the steering to the F1 sine 50, so it will give you counterclockwise position. That's why the value of the torque number 1 is positive, while the value of torque number 2 is negative. Okay, and the net torque, and which direction does the wheel turn as a result of these two forces? Of course, there will be significant forces between torque number 1 and torque number 2. So it will give a resultant force, which is the net force is based on torque number 1 plus torque number 2. So 41 Newton meters plus with 41 Newton meter plus with a negative 43. So you will get negative 2. So negative 2 basically clockwise or and counterclockwise. The answer is it will follow whatever happens to the negative. So the negative, so the final answer is negative. That means the wheel with the steering wheel, the ship's steering wheel be turned to clockwise positions. Okay, because the final is negative. Okay, right. So right now, look at the swinging doors. Okay. Let's look at if the man applies a force of 300 Newton, at an angle of 60 degree to the door. Okay, 60 degree to the door. In figure 8.7, which is this one, 8.7a. Here, okay, 2 meters from the hinges. Okay, 2 meters from the hinges. So this is the hinges. Okay, this one is a doorknob, right? So he applied a 300 Newton at 60 degree, slightly have some angle there. Okay, choosing the position of the hinges as the axis of rotations. Okay, so find the torque on the door, choosing the position of the hinges as the axis of rotations. When we're discussing about torque, we should know one thing, except, okay, you should know about lever arm or radius. Okay, you should know about force. Okay, that means the applied force to the radius. Okay, and you should also know where is the center of rotations. Okay, because if you want to calculate the lever arm, or if you want to calculate the R in the torque equals to RF sine theta, R is exactly from the center to the force. From the center to the force. That's why we need to establish first which point is considered as the center of rotation, because from that we can calculate the R. We can give the value of R. Okay, because the value of a center of rotation can be changed from situation to another situation. Okay, so you will look later on what will happen when we change the center of rotations. Okay, so right now the hinge, okay, that means angsel di tepi pintu tu, angsel, okay, will be the center of, or the axis of rotations. So that means we consider that thing, therefore we can calculate R as 2 meters, because of course, when we want to apply, we want to open or to close the door, okay, we will use this doorknob. Okay, and this person, okay, this man, we apply some 300 newtons at 60 degree. 300 newtons at 60 degrees to the door. Okay, so how we can calculate that? All right, so 2 meters as R, and F is 300 newtons, sine 60. Why sine 60? Here. Okay, if you look carefully, this one is 300 cos 60. And we don't want this one because it is a parallel to the lever arm. We want that perpendicular to the lever arm. So that's why the answer is 300 sine 60. Times we get 520 Newton meter. Look at the unit, 520 Newton meters. Okay, and part B, suppose a wedge is placed. Okay, a wedge is placed 1.5 meters from the hinge on the other sides of the door. On the other sides of the door. So we place a hitch, macam penahan pintu lah. Okay, penahan pintu. 1.5 meters from the hinge. So 1.5 meters slightly here. Okay. And of course, if you try to put that way, the force, so the hinge will be here, like this. Okay. What minimum force must the wedge exert so that the force applied in part A won't open the door? Won't open the door, that means the door is not moving. The door is not moving. It cannot be opened. So that's why we need to make sure that thing first. Okay. So right now we have doorknob, which is our force here, and we have hinge, okay, the torque at hinge, and we have the torque at wedge. Okay, when we talk about torque, okay, when we're discussing about torque is applied to all forces involved in one particular situation. Okay, you should know, like the one that we did here. Okay, we should calculate all this on all forces, force number 1 and force number 2. Is there any other force? No. Okay, it's just involve F1 and F2. Okay, F1 and F2. If there is some F3 here, then we need to calculate the F3 also. So that's why we need to consider every forces. So in this case of the doorknob, okay, have one force. The hinge itself is considered to have one force. But okay, when we talk about the top of the hinge, it becomes zero. Why the top of the hinge becomes zero? Because we considered, okay, if you look carefully, if we try to calculate the torque of the hinge, RF sine theta, but we have choose the axis of rotation to be at the hinge itself. Dia duduk dekat situ je, axis of rotation. Therefore, R dia akan, torque dia akan jadi kosong. Why? Because R dia kosong, jarak dia tak ada. Okay, so everything that you put, okay, that relates to the force, you need to calculate everything. So that's why this man is applying with a certain force, and of course when he puts some wedge at the end of the door, at the end of the door, at the back of the door, okay, in order to hold the doors so that it cannot be opened. So that is also considered to be force. This one is force. This one is also force. Hinge is also force. But when we calculated torque to the hinge, so this torque of hinge becomes zero because R is zero. Okay, so that's why when we combine everything, so we can have a submission of torque equals to zero. Okay, so right now we can use the term submission of torque equals to zero. So what is submission? That means hasil tambah all torques. Okay, kesemua torque yang ada, kena cari dia punya hasil tambah dia equivalent to zero. That means it is in static equilibrium. Static equilibrium. How can I know this one is a static equilibrium? Because the door is not moving. Okay, because the door is not moving, you cannot open the door because of the wedge you put at the back of the door. So that means if he try to pull to push the door, it cannot be opened due to that wedge. So what minimum force must the wedge exert so that the force applied in part A won't open the door? So we can use that equivalent, you can use that force from part A. So you look carefully, this is the top of the hinge plus with the top of the wedge and the top of the force. So top of the hinge is 0, and look at how they write down the top of the wedge. The top of the wedge is RF, okay, sine 90. So this is R, this is F, the one that we want to calculate here, F, sine negative 90. Why sine 90? Okay, because wedge is exactly at the back of the door, so it will be going that way. Okay, it will be going down, not going down. Actually, the force of the wedge is oppose the motions of the force. We try to open the door, we try to push the door to this side, okay, to the other side, so the door will open. Okay, if you in our words, okay, we try to make the door becomes counterclockwise, okay, because the door will be here, okay, will be moving like this counterclockwise, but the wedge is actually hold the door so that it won't be open. So the wedge will be in the position of clockwise. So that's why the negative value here. Okay, so you don't have to put that negative. Just calculate the, but you need to put the negative value to the value. Okay, so plus with the 520 Newton meters. So in the end, we'll get that the wedge, the force of the wedge is 3,347 Newton. 347 newtons. Okay, remember the force is going other way than the force of the wedge. Okay, so we are saying that the force is try to open the door, but the force from the wedge will try to hold the door from open. Okay, so in other words, when we try to learn about torques, okay, it's actually can help us to understand force a little bit more. Okay, right. Right. So these are the thoughts and the two conditions of equilibrium. Two conditions of equilibrium. Before this, when we have a equilibrium situation, okay, that means if you try to hold some, let's say, this one is picture using some cable. So you can see here, okay, the frame of the picture. Let's say the picture. This one is a picture. The picture is not moving. Okay, when we are applying some cable. Okay, so this is where we can apply that summation of fx equals to 0 and summation of fy equals to 0. But right now, when we're discussing about torque, you have already discussed about torques. You can apply the net torque acting on the object, okay, which is the object, okay, is static. So we can also apply summation of torque equals to 0. Same thing happens in here. Summation of torque equals to 0. Okay, right? So this is actually can help you a little bit more in order to establish some equation, because the main problem is when you have 2 or 3 unknowns, so you need to come out with the equations. Okay, because when you have 3 unknowns, you need to come out with the 3 equation at least. So in what way to get that some equation? Right now we have one more situation, which is summation of torque equals to 0, except from a summation of fx and summation of fy equals to 0. Okay, so look at these examples. Okay, I don't want to do this example first because it's quite, it doesn't give some value. Okay, I think this one is good. Okay. After this, then we go to that part. Okay. A woman of mass M equals to 55 kilograms sits on the left end of the seesaw, a plank of L. Okay, that means a plank L, all right? Okay, which is 4 meters, pivoted in the middle as in figure. Pivoted. Okay, that means some pivot. Okay. If you try to imagine, this is kind of where you can use a lever, type 1, type 2, or type 3, where you can put a load and you can put a force where there is a fulcrum. Okay. So pivoted in the middle as in figures. First, compute the torques on the seesaw about an axis that passes through the pivot point. Where should a man of mass M 75 kilograms sit if the seesaw plus man and woman is to be balanced? Is to be balanced. The word balance means here. Okay, that means every torque is equivalent to 0. Okay, summation of torque is equivalent to 0. This is how they write down the equations. And then they go one by one. Everything that considered have force must be equivalent to, must be counted as torque. Remember, every forces. For example, okay, look at how they write down. The torque of the pivot, this one is a pivot. The torque of the gravity, okay, where comes the gravity? The gravity of the plank, because the plank also have some maybe, yeah, maybe will have some mass. If the planks have some mass, therefore we need to calculate its gravity. Okay, this is considered to be force. The pivot is also have some force. In this case, they use normal force. Okay, right? And the force from the man and also force from the woman. This is how they write down the summation of torque equals to 0. Okay, so let's say, we take the point of the pivot, okay, in the middle as the axis of rotation. Remember, torque is equivalent to RF sine theta. RF sine theta. That means R is the lever arm. or the distance between the force and also the center of rotation. But if we take this one as the center of rotation, it will eliminate the torque of the pivot and also the torque of the gravity. Why? Because R is 0. Simple. Okay, this one because of why? R 0. R 0. So that's why it becomes 0. What happened to the torque of the man? Okay, the torque of the man is going to be to the bottom, and the torque of the woman also to the bottom. But if you look carefully, why men and women will have a positive or negative? So that depends on the situations. Because the man is on the center of rotation is on at the left of the man. Okay, duduk di sebelah kiri lelaki tu. While the center of rotation duduk di sebelah kanan perempuan tu. Okay, on her right side. Okay, so with that case, okay, we are applying, let's say this is the rotation, so the man is actually clockwise. So that's why the man will have negative value, while the woman, okay, so this is R, is actually going this way. It's a counter clockwise. That's why it have a positive value. Okay, how do I know in order to get the clockwise or counterclockwise? Okay, just use some ruler. Okay, just use some ruler. Okay, for example, here. Okay, just use some ruler. Okay, let's say this is your center of rotations. Okay, center of rotation. So you use some ruler. Now, at the one point of the ruler, you point at the center of the rotations. Okay, you put your ruler, letakkan ruler kamu di tempat center of rotation. Letak dia sebaris lah kan. Okay, if the force is going this way, ke bawah. Okay, now cuba tarik salah satu daripada letak ruler tu. Okay, satu letak di center of rotation, satu lagi letak ruler tu pada sebaris dengan force. Okay, so maksud dia, your ruler should be here, like this one. Okay, should be here. Okay, so cuba tarik kawasan ruler ini. Cuba tarik kawasan ni ke bawah. Try to pull or try to push this. So right now, yang ni hold. Pegang dia dekat center of rotation, pegang dia. Okay, so you can see that your ruler will be going this way. So that's why I know that this one is a counterclockwise. In the lessons of torque, this counterclockwise or clockwise position is very, very important in order for us to put the negative or positive. Okay, for example, let's say if you have some force is going that way. Okay, now you put your ruler or your pencils over here and then hold this thing, always hold at the center of rotation, and then push the ruler at according to the force. Okay, if the force is going up, then push your ruler upwards, and then you will get to see that this one is the direction of your ruler. So that means it will rotate counterclockwise. If let's say here the force is going down. Okay, let's say force here. Now you hold your ruler, and then the force will be going here. You should put your ruler over here. Then the force will be going this way. So that means the force is clockwise. Then the torque will be clockwise. When the torque clockwise, you get negative. The torque and counterclockwise will get positive. So let's do some things here. Okay. Alright. So that's why from here we can get the value of, let's say this is mgx. Why? Mg, this man is x from the center of rotations, which is m times g times x. Okay. And this girl is, okay, provided that it is at the center, okay, in the middle. Middle means pivot tu duduk di tengah-tengah. So we can say that mgl over 2. So you can manage to get x equals to 1.47 meters. 1.47 meters. Okay, part B. Find the normal force exerted by the pivot if the plank has a mass of, okay, in the second situation, which is slightly different from A, part B, the plank has mass. Okay, this is the good where you can apply some equations that involve mass of the plank. The mass of the plank is 12 kilogram. So when there is some mass, so meaning that we can calculate its force because m times with the gravitational accelerations, so you will get to force. Okay, so now we have mg. Let's consider everything. The normal force is going upward, the mass is going downwards. Okay, this girl is also downwards, so you can see this is the man, the girl, m plank g, and the normal force. Okay, and normal force is going up, and because of that, it is a positive value. Everything 1, 2, 3 negative, and normal force is going up. Okay, negative, 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 and lastly positive. And the normal force will be 1390 Newton. 1390 Newton. And lastly, repeat part A, but this time compute the torque about an axis through the left end of the plank. Look at how they did. Okay, left end of the plank. Okay, repeat the part A. You look at two different things. Okay, and in part A, they consider that the pivot, okay, as a center of rotation, duduk di tengah-tengah. Tetapi dalam part yang ketiga, which is part C, dia nak letakkan di sini sebagai center of rotation. You look carefully, the top of the woman will be 0. Nampak Top of the woman will be 0 because F kali dengan kosong. R dia kosong. Tetapi untuk orang lain ada value. Plank ada value, normal force pun ada value. So, jalan kira dia sama juga, jadi lebih panjang sedikit je berbanding jawapan dengan part A. Sama juga jawapan dia. Okay, lebih kurang sama. 1.47, 1.46. The X is still 1.47 and 1.46. Okay, so jalan kita akan menentukan tempat mana yang akan bagi kita kesenangan untuk jawab soalan torque. Okay, it's either you can use the center. Normally, we need to use center of rotation dekat tempat yang paling banyak force ada kat situ. Okay, for instance, this one have normal, this one have plank, mass of the plank, so tempat tu lah yang biasanya jadi. Kalau tempat lain dia ada satu tempat, then we need to calculate everything. The pivot, the normal force, but right now, if you choose, then you can eliminate both. Kita dah eliminate dah dua-dua sekali. Okay, right. This is very good examples of balancing. Okay, let's go back to this part. Okay, so let's go back to this part. A child of mass m is supported. Okay, I don't want to go this part first. I may use the same equations, but I want to discuss here. Okay. Zero torque and the static equilibrium. Again, I would like to highlight it. The net force acting an object must be 0. Okay. Summation of F is equivalent to MA. But if A is 0, then summation of F is equivalent to 0. Okay, so mana dapat dia 0, 0, 0 ni sebab acceleration kosong. Okay, 0 in acceleration, therefore the summation of force will be equals to 0. And what summation of force? Now it divided to Fx and also Fy. If the object doesn't move in X and also in Y, then everything is considered to be 0. Because of that, kita namakan dia static. Okay, and then right now, okay, after we can apply also the submission of torque equals to 0. Normally, okay, we will use a lot of summation of torque equals to 0. First, sebab apa? Sebab dia paling banyak boleh calculate something. Okay, tetapi submission of fx and submission of fy boleh jadi pembantu kepada submission of top equals to 0. Okay, alright. So that's why it's very good to understand this one. Okay, if the net torque is 0, it doesn't matter which axis we consider rotation to be around. We are free to choose the one that makes our calculations easiest. So mainly, okay, we will take maybe at the one in the middle or the one at the end. Just make sure that you should point or you should put the axis of rotation at least at one of the force. Don't think a very advanced way like this. For example, okay, the child is not in the middle, but I want to take this one as the center of rotation. Okay, very bad idea, because right now we need to calculate F1, we need to calculate mg, we need to calculate F2. If you put center of rotation F1, then you don't have to calculate the torque F at F1. Just make sure about the boy and also the man. If you take at the child, then you need just to calculate just to torque. So that's why we need to choose our center of rotations in order to make our calculations easy. Okay, so these are the zero torque and the static equilibrium. So right now, a child of mass m is supported on a light plank by his parents, who exert the force F1 and F2 as indicated, which means F1 and F2 is going up because the child just sit on the plank, and of course it has some mass. Find the force required to keep the plank in static equilibrium. Okay, if we look at the question itself, okay, it mentioned here light plank. Why it mentioned light plank? Because we don't want to calculate its mass. Okay, when light maksud dia sangat ringan. Bila sangat ringan, we can ignore the mass of plank. Tak nak jadi macam tadi. Tadi kan dia calculate plank. Okay, menggunakan. So, sebab plank ada mass, kita terpaksa calculate dia punya torque. But in the light plank, we can eliminate it. So, we just consider every forces yang kita nampak. So, that's why di dalam bagi tu dia mention about light plank. Okay. So, use the right end of the plank. Use the right end, okay? It's stated here in the question, use the right end of the plank as the axis of rotation. So, when we apply this point as an axis of rotation, then we need to consider the baby and also the mom, F1 and mg. Okay, and of course, this boy have a quarter of L, and his mom is a third quarter. Okay, we'll have a third quarter L. Okay, so therefore, if you look carefully, they started with the because of the force is all in the x and y axis, so they use first the submission of Fy equals to 0. So F1 going up, F2 going up, minus mg going down, equivalent to 0. So another equations that they consider is the torque, submission of torque equals to 0, which is negative F1L, which means negative F1. How can I get negative? Because if you try to apply some ruler here, okay, you hold at the center of rotations, okay, your ruler will be going up based on force. The force is going up, is going to the clockwise position, so that's why it becomes negative. And the boy will become positive, mg times with 1/4L, and then you will get that the F1 is equivalent to 1/4 mg. And obviously F2, okay, when you calculated F1 and you calculated F2, F2 is what? Then refer back to this part. Okay, F2 is equivalent to mg minus F1, and F1 is half mg. Quarter mg. So therefore, the answer is third quarter mg for M2. F2. these are some zero torque and static equilibrium also. Okay, for examples, don't walk under the ladder, find the forces. Okay, this is very good for examples regarding the zero torque and static equilibrium. Okay, let's look at this example first. Okay, an 85 kilogram person stands on a lightweight. Okay, let's use the word lightweight. That means we don't have to bother about the mass of the ladder. You just maintain what it is. The floor is rough. The floor is rough. That means there must be some friction. Mesti ada friction bila dia kata floor. Okay. In this case, kalau kita tengok dalam situasi ladder ni, dia akan ada, this one is known as floor. And this one is known as wall. Ni wall. Wall dekat tepi. Floor dekat bawah. Okay. Banyak signifikan dia ya. So the floor is rough, hence it exerts both a normal force F1. Look at how they write down F1 as a normal force. So dalam case ni dia tak guna N lah, dia guna F1 and frictional force F2. Kenapa frictional force F2 ke arah situ? Sebab ladder ni kalau dia letak di atas floor ini, dia akan terslip ke bawah kan. Kalau kita letak tangga biasanya, dia nak terjatuh ke sana kan. So bila nak jatuh ke sana, motion dia sepatutnya gerak ke sana, tetapi dia sebab ke arah sana, tapi sebabkan friction dia akan lawan arah. So this is the friction. So that's why F2 ke arah situ. And the wall on the other hand is frictionless. Okay, the wall frictionless. So dia tidak ada apa-apa lah, tetapi dia ada normal force. Look at how they write this normal force. So F1, F2 and F3. F1, F2 and F3. Okay, normal force is 90 degrees to the surface. Okay, using the dimensions given in the figure, find the magnitude of F1, F2 and F3. Menggunakan apa? Summation of Fx equals to 0, summation of Fy equals to 0, summation of F torque equals to 0. So dalam case ini, macam mana dia buat dulu? Okay, dia menggunakan summation of F torque equals to 0. Okay, kenapa dia guna summation of F torque? Katakanlah this one is taken to be center of axis of rotation. Axis of rotation. Maksudnya kita dah tak perlu calculate F1 dengan F2, dia memang akan dapat kosong. Kita hanya calculate mg dengan F3 sahaja. So mg dengan F3 sahaja. So F3 kalikan dengan A. Okay. Kenapa kita boleh kali macam tu? Sebab dia ambil ini. F3 dah arah sini, komponen dia yang perpendicular. Sekarang ni dia tidak bagi berapa ketinggian tangga. Dia tak bagi, ada dua case dalam kes ini dia tak bagi berapa ketinggian tangga tu. Tangga tu jarak dia daripada bawah ni tak tahu berapa. Dia just bagi tinggi dia dengan dia bagi panjang dia je. Jadi kita boleh gunakan A ni dikalikan dengan F3, dapatlah jarak dia dapatlah jarak dia, which is nampak kat sini dia dah 90 degrees dengan yang ni. Okay, so F3 kali dengan A minus dengan mg ke bawah, so kita kalikan dengan ini 90 degrees dia 0.07, so equivalent to 0. Okay, so that is one equation. And number two, kita solvekan dulu sebab mg sama dengan berapa jawapan dia tu, A sama dengan 3.8. Okay, kita bawa pergi sebelah sana, selesaikan dulu 3.8 dan dapat 150 Newton. F3 is equivalent to 150 Newton. Okay, because ni kita bawa ke sana bawa ke sana. F3 equivalent to mgb over A. Okay, so equivalent to 150 Newton. Alright, so kita tengok right now F3 done. Okay, but in x-axis, tengok sampai ada kat x-axis, kita ada F3 dan kita ada F2 sahaja. So, we can use summation of Fx equals to 0. So, F2 tolak dengan F3 equivalent to 0. F2 sama dengan F3. So berapa jawapan dia? 150 Newton. How about F1? Okay, F1 is going up. Yang ada pada arah dia ialah mg dengan F1 je. So summation of Fy equals to 0. F1 minus mg equals to 0. F1 sama dengan mg. So the answer is 830 Newton. Okay, it's quite different compared to this part. Okay, kalau kita tengok examples next, berbeza sedikit. Kenapa berbeza? Sebab tadi tangga tu panjang dia tidak diberikan. It doesn't give you the it just give you the height of the ladder, but not the length of the ladder. Panjang dia. But in this question, it give you the length of the ladder. So therefore, we can apply the three things: summation of fx equals to 0, summation of fy equals to 0, and the main thing is summation of f top equals to 0. Okay, so let's look at these examples. A uniform ladder 10 meters long and weighing 50 Newton rests against a smooth vertical. Okay, a uniform ladder and weighing. That means the ladder have some mass. Okay, in this case, they have weight this one as 50 Newton. So maksudnya ladder itu ada dia punya berat dia sendiri. Macam biasanya tadi light plank dia bagi tahu, mention light plank. Okay, lightweight ladder. So kita tak border dia punya value. Tapi sekarang ni kita border dia punya value disebabkan oleh dia mention mengenai berat ladder. But smooth vertical wall. Smooth vertical wall, that means tidak ada no friction. So no friction, just involve a normal force. Normal force lah daripada wall. If the ladder is just on the verge of slipping when it makes a 50-degree angle with the ground, find the coefficients of static friction. Let's look at the situation. It can also involve static friction. Bukan main-main, because bila involve dengan force, we can also put a static frictions together. Okay, so the main criteria here, we have friction, we have normal force, we have normal force on the wall, and we have weight of the ladder. Okay, so in the end, we can apply. Okay, we can apply some force. Let's say we use first the summation of fx equals to 0, which ke arah kanan ada friction, ke arah kiri ada normal force. So friction and normal force is equivalent. Tapi tak jawab lagi apa-apa kan. Okay, because dia nak suruh kita cari coefficients of static friction, which is nak cari mu s. Mu s maksudnya kena dapatkan dulu fs dia. Fs kena dapatkan dulu mu s baru boleh dapat ni. Maknanya kena tahu mu s berapa, kena tahu normal berapa, baru boleh dapat mu s. Okay, right? So the Fy, siapa yang ada? Okay, Fy ada 50 Newton dengan normal force. 50 Newton and normal force. So N minus 50 equals to 0, N equals to 50. Right now, kita dah dapat dah berapa nilai normal force, 50 Newton. Okay, using this, the other submission of torque equals to 0. So we take this part. Okay, we take this part as the center of rotations. So we eliminate, okay, normal force punya torque. We eliminate the frictional punya torque. Yang tinggal hanyalah top of the ladder and also the normal force. So ada dua je torque, which is yang 50 Newton tu dengan normal force saja. So dalam kes tu kita dapat jawapan normal force on the wall ialah 21 Newton. So dari in the end kita boleh calculate dia F equals to mu Sn. Okay, so mu S ialah F bahagi dengan N. F tadi 21 Newton divided by 50 Newton. So therefore we get 0.42 value. A lot of questions can be applied, okay, when we deal with the torque. Okay, so let's look at one examples here. A weighted forearm. Okay, a weighted forearm. A 50 Newton bowling ball is held in a person's hand with the forearm horizontal. Forearm horizontal. Okay, this one horizontal. Dia straight dulu kat atas. As in figure. The bicep muscle, which is here, bicep, ketul dulu. Bicep muscle is attached to 0.03 meters. 0.03 meters. Ni jarak di antara ni dengan hujung siku kita lah. From the joint. Joint ni kita punya siku lah. Okay, joint, and the ball is 0.35 meters from the joint. Okay, ball duduk 0.35. Bicep so diikat 0.03 meters. Find the upward force exerted by the biceps. Okay, yang ni lah. Kalau kita tengok dalam lukisan sebenar macam ni lah. Tak adalah dia ambil sengit macam ni, dia ambil straight lah. Okay, consider force of the bicep to straight line. Okay. And the downward force exerted by the humerus on the forearm. Okay. Disebabkan joint kita ini di sini, so akan ada satu downward force. Downward force tolak dia. Sebab itulah kita kata dekat sini ada bola, ada 50 Newton, ada biceps yang dapat tarik benda ni daripada downward force. So ada downward force, ada 50 Newton and ada biceps. Ada 3 benda dekat situ. Okay. Neglect the weight of the forearm. Okay, neglect. Maksudnya kita tak perlu cari calculation untuk torque untuk forearm. Okay, torque untuk forearm kita neglect dia. So hanya ada 3 force sajalah. 50 Newtons, okay, downward and also biceps. Right? So find the upward force and the forearm. So, maksudnya kena cari 2 equation dekat sini. First equations kita menggunakan summation of torque. So summation of torque kita ada forearm, kita ada bicep, kita ada ball, dan kita ada downward force punya torque, kita ada biceps punya torque and also bowling ball punya torque. Ada 3 sekali. Tetapi bila kita ambil dekat sini sebagai axis of rotation, automatically downward force akan hilang. Okay. Yang anda tinggal adalah ini dan ini sahaja. So in the end, we will get the force of the bicep, which is equivalent to 583 Newton. And using the summation of Fy equals to 0, so you will get F minus R, okay, because F is upward, R is downward, and 50 is downward also, so you will get the downward force equivalent to 533 Newtons. Okay. Okay, we may look at some situations here. Okay, it's about walking a horizontal beam. A uniform horizontal beam 5 meters long and weighing 300 Newton is attached to a wall by a pin connection. Maksudnya ada pin connectors tu that allows the beam to rotate. So beam tu sebenarnya boleh move around. Okay, boleh rotate ke atas, ke bawah. Sebab dia hanya pin saja. Right. Tetapi dalam pin pun kita support dengan cable. Its far end is supported by a cable. So this cable, so maksudnya ada satu tension ke atas sana. Okay, that makes an angle 53 degree with the horizontal. Okay. If the person weighing 600 Newtons stands 1.5 meters from the wall, find the magnitude of the tension T in the cable and force R exerted by the wall on the beam. Okay, ini situation dia. Daripada situation A, kita kena jadikan dia situation B. Sebab situation A tidak memberi apa-apa indicator. Where is our force? Tetapi yang kita faham ada tension. Dan kalau ikut dengan situation ini, plank yang diberikan itu ada berat dia, which is 300 Newton. So we need to calculate. Dan kenapa kita letakkan di tengah-tengah? Normally, weight, apa-apa pun, we must put it at the center. This is the weight. Macam tu kita letak. So every time we see plank, we see symmetrical objects, normally the center of the weight is actually from the center of the things, of the material. Duduk di tengah-tengah tu sebenarnya. Alright, and then it must be going downwards due to the gravity. If a person's weighing 600, and then we need to find what is our T and what is our R. And the R is going that way. Kenapa dia sengit macam tu Yes, because of the situation depending on here. Dia datang daripada sini dengan daripada sini. Itu je lah dia. That's why R dia dapat macam tu. Dia akan ada RX and also RY. RX and RY. So ini situation dia, tetapi bila dipindahkan menjadi ini dan kita akan jadi lebih faham. Okay, so there is some T sin 53, T cos 53, 300, 600, RX and RY. So in order to calculate that, okay, right now kita nak ada 3 benda dekat sini. Kita nak calculate what is RX, RY, dan kita nak calculate what is T. Kena ada at least 3 equations. Okay lah, because we have summation of T, summation of Fx, and summation of Fy. Okay, so right now, this is summation of torque. Normally, if you look at the question, it always starts with the summation of torque equals to 0. Okay, summation of torque. This one is based on RB, based on R, based on beam itself, based on man, based on T tension. Itu dia situation dia. So untuk torque ini, kita tak boleh nak tengok dia detail. Kita just calculate based on, bila kita ambil dekat sini center of rotation, R akan jadi kosong. Okay, beam akan jadi WB kali dengan half L. Okay, ini ada value, ini ada value. Yang ni akan jadi man is 1.5 meters, ini ada value. Dan TL yang paling hujung sekali 10 tension. T kali dengan L sin 53. So itu je saja 3 tu. And then we solve it here, we can get T equivalent to 413 Newton. 413 Newton. Okay, so tak selesai lagi because we need to find what is R. Okay, then we apply some summation of Fx equals to 0 here and summation of Fy equals to 0 at number 2. Okay, so that will give you Rx and Ry. Okay, all right. So today we have learned about torque, the situation of torque and the conditions of torque, which is summation of torque equals to 0, and the conditions when we apply force, which means the static equilibrium. So what is the conditions of static equilibrium? Summation of Fx equals to 0, summation of Fy equals to 0, and summation of torque equals to 0. And again, torque is equivalent to Rf sin theta. Rf sin theta, where the lever arm or the radius is multiplied with the component of force that perpendicular. Okay, component of force that perpendicular to the lever arm. Okay, perpendicular to the lever arm. That's why we are getting the value of torque. And the unit for torque is Newton meter. Okay, don't forget the unit of torque is Newton meters. Okay, I think that's all for today. And the conditions when we apply force, which means the static equilibrium. So what is the conditions of static equilibrium? Summation of Fx equals to 0, summation of Fy equals to 0, and summation of torque equals to 0. And again, torque is equivalent to Rf sin theta. Rf sin theta, where the lever arm or the radius is multiplied with the component of force that perpendicular. Okay, component of force that perpendicular to the lever arm. Okay, perpendicular to the lever arm. That's why we are getting the value of torque. And the unit for torque is Newton meter. Okay, don't forget the unit of torque is Newton meters. Okay, I think that's all for today. Okay, can you hear my voice? Boleh dengar suara saya?
Boleh, sir.
Yes, sir.
Yeah. Okay. Okay, I may continue a little bit from this chapter. Okay, so stay tuned. Right, let me share the slide. Okay, so this one is taken from the same topic. Okay, the torque and the angular acceleration, the torque and also the angular acceleration. Okay, so in this part is just some extended versions of the torque. Okay, so before this we have learned torque. In terms of torque is equivalent to Rf. Okay, that means R multiply with F, or R dot product F, Rf. So it is also equivalent to Rf sine theta. Okay, but what happened when we try to consider torque and also angular acceleration? Okay, if you look carefully, torque is just a torque. Okay, that means you can relate these things to the force. Okay, that if it's linear, then torque will be force, while the angular acceleration is alpha. The angular acceleration is alpha, and alpha can be comparable to acceleration. Okay, so without cause between acceleration and force, okay, we can actually derive the Newton's second law, which is summation of F equivalent to ma. So if you put that acceleration equivalent to F over m. So how can we relate some things that related to alpha and torque with, and also A and F? Okay, so first of all, okay, so this is given by the Newton's second law. F equals to ma, and A is equivalent to F over m, right? And at the same time, we have known that acceleration is given by R alpha. Okay, from the previous lesson, A equivalent to R alpha, while alpha is equivalent to A over R. Okay, alpha is equivalent to A over R. Okay, and then if you try to combine the things, or you try to put it here in terms of F equals to ma, so we may simplify the things that we can relate that the alpha, okay, because here is A equals to F over m, you can put A F over m over here, F over m over R, and it becomes alpha. And of course, if you want to eliminate some R over here, we need to multiply both with the R. And therefore, we can have alpha equivalent to Rf over mr squared. Okay, Rf equals to over mr squared. And if you noted here that Rf is actually a torque, and mr squared is actually something else. Okay, so that something else is equivalent to this one. Okay, so Rf is torque, and mr squared is considered to be moment. Moment. Okay, sometimes they call it as moment of inertia. Okay, moment, or sometimes they call it moment of inertia. That means we can relate radius and also mass. Radius and mass. Mr squared, I equals to mr squared. Therefore, we can form one equation that involves torque and alpha, that is equivalent to torque equivalent to I alpha, where this is torque. Okay, this one is angular acceleration, and I is the moment of inertia. Okay, we have torque, we have angular acceleration, we have moment of inertia. So torque equals to I alpha. Okay, if you try to compare this value, these things, it is actually the same as F equals to ma. Okay, because we can compare torque to force, we can compare A to the acceleration, alpha to the acceleration, And by the time this moment I is comparable to mass, because mass times with radius. Obviously, before this, let's say you have A is equivalent to I alpha, R alpha. Okay, V equals to R omega. Okay, you look at all the acceleration. If you want to get the angular acceleration, you just multiply with R. Same goes to I. Okay, but if you look carefully in terms of torque is quite different, because torque is R times F. Okay, that means you multiply with F with the R, and then we'll apply the I is equivalent to mr squared. Okay, that means you multiply mass with the r square, then you can get moment. And of course, moment is depending on the situation. Okay, will depends on the situation. What kind of situation? Here, these are the moments of inertia for various rigid objects of uniform composition. And of course, it is not the same as I. With the general equation is I equals to mr squared. But if you look carefully, okay, if you do have some uniform objects, okay, uniform objects. For example, we have a solid sphere. Okay, we have solid sphere, same like guli. Yeah, solid sphere. We have hoop or thin cylindrical shell. That means we have cylindrical shell, and inside is a hollow. Okay, that is equivalent to mr squared. I equals to mr squared. The solid sphere is I equals to 2/5 mr squared. The solid cylinder is like a solid of cylinder or disc, okay, that have R. Okay, so that means half mr squared. The thin spherical shell is like a hollow in the shell, but it's in the form of sphere, but have hollow. And also have two long thin rod, okay, long thin rod that have a possible two axis of rotation. Okay, on the left side is the where it is rotated at the center. This one rotating at center, and this one is rotating at the end. This one is taken in your textbook survey. Okay, so do you need to memorize all of these equations? Definitely no, because we will provide all the equations such as according to the we will provide all the equations according to the problems, because when we given you problems, we will give a moment of inertia. Okay, or maybe you need to calculate the moment of inertia. Okay, so at the end you need to calculate the final is to calculate the moment of inertia, so you don't need the equation, just need the value. Okay, but if you are required to calculate the moments of inertia, we will provide the equations. Okay, we will provide the equations inside the questions. Okay, so don't worry about that, right? So for example, this question. Okay, a baseball player loosen up his arm before a game, tosses a 0.15 kilogram baseball using only the rotation of his forearm. Okay, of his forearm, forearm, lengan. Alright, has a mass of 1.5 kilogram and a length of 0.35 meters. Okay, the ball starts at rest. Okay, you can see the ball start at rest. Okay, with the initial velocity 0, and it's released with a speed of 30 meters per second in 0.3 seconds. Okay, that means you can measure some acceleration there, because initial velocity 0, the final velocity is 30 meters per second in 0.3 seconds. Find the constant angular acceleration of the arm. Basically, we need to calculate the alpha. Okay, so in order to calculate the alpha, we may use some equations using the angular equation like this: omega equals to omega naught plus alpha t. So using that value, so you may get 286 radian per second square. Okay, So that is number one. And the part B is calculate the moment of inertia. Okay, calculate the moment of inertia. Okay, as I said earlier, okay, if they want you to calculate, they didn't have to put the, they did not put the equations inside the questions. Okay, because they want you to calculate the moment of inertia. Okay, calculate the moment of inertia of the system consisting of the forearm and ball. Forearm and the ball. Okay, so number B is you need to find the moments of inertia. Okay, so the ball is considered to be a baseball is actually have mr2 square. Okay, mr2 square. Okay, here is the ball, because we know that it comes from the 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 the, the shape of the ball is actually a round. Okay, it's like some sort like sphere. Okay, so we can use mr squared, right? Or you can use the value. So the forearm, okay, the forearm is 1/3 ml square, because we are rotating the forearm. Forearm is like a long thin rod, okay, long thin rod, but it is rotating at the end of it. So we may use 1/3 ml square. Okay, 1/3 ml square, right? So 1/3, 1.5 kilogram times with 0.35 meter square. So you will get to the value kgm square. And then we add up to everything, then we can get the a moment of ball plus the moment of forearm, that is equivalent to 7.97 10 power of -2 kgm square. Look at the value of the moment, which is kgm square. Okay, all in the denominator, in the numerator part, kgm square. And then lastly, find the torque exerted. Okay, the torque exerted on the system that results in the angular acceleration found in part A. So use that value, torque equals to I alpha. So you get this value, I, and calculate the torque. So you put that alpha here. So we just calculate 7.97 10 power of -2 kilogram meter square times with the radian over 286 radian per second square. Okay, so in the end, we will get torque in terms of Newton. Okay, Newton meters. Okay, can do on your own, right? This one is another exercise. Okay, a light rope wrapped around a disc-shaped pulley. A disc-shaped pulley. Okay, a disc-shaped pulley is pulled tangentially with a force of 0.353 Newton. Find the angular acceleration of the pulley. Okay, so first of all, applied torque will be from here we have torque equals to R. Okay, R F. So we will get 5.8 10 power of -2 Newton meters as our torque. And then because of that, the pulley, this shape pulley is based on half mr squared. Okay, so you will get 7.9 10 power of -3 kgm square. Okay, use this equation, half mr squared. Okay, of course it is not stated in the question, but when normally okay, just normally in our practice, okay, maybe we may put that initial for the moment of let's say this one is this, okay, is equivalent to half mr squared, like this. Okay, so they will put that moments equations, or maybe they will give this equation inside the appendix, but don't worry about the other equations. Okay, so half mr, m is mass, r is the radius. So in the end, okay, the question asks you about find the angular acceleration. So torque equals to I alpha, alpha equals to torque over I. Then you will get 7.3 radian per second square. Look at how they write the equations. Newton per meter, kgm square. So in the end, you will get radian per second square. Everything must be in SI unit. Okay, although you cannot easily cancel out, okay, up and down, okay, but the answer should be radian per second square because it should be based on alpha. Okay, but remember, do it everything in SI unit. For example, meter, okay, in meters, right? Don't use centimeters if the question give you centimeters. Okay, so once again, we have analogies between linear and angular motions. Okay, before this, we have a V that be comparable to omega. We have we have X or Y that can be comparable to theta, and we have A that is comparable to alpha. But in the analogies between linear, that some today, okay, we learn about linear quantity can be comparable to moment, A can be comparable to alpha, and force can be comparable to torque. Okay, so here we have from the previous lesson, V to omega, X or Y to theta, and alpha A to alpha. Comparable, okay? All right. Okay, let me skip this thing first. Just do this one. An object has a moment of inertia of 5 kilogram meter per second. So this one should be your I. And about a fixed axis, a torque acts on the object initially at rest, so that the angular acceleration, angular velocity of the object increase at a constant rate 306 rpm in 6 seconds. Okay, so meaning that here they want you to find what is alpha based on omega minus omega naught divided by t. Okay, but you need to convert the RPM towards into radian per second first. Okay, determine the magnitude of torque. Okay, because of that, okay, after that you want to find what is the torque equals to I alpha, because torque is I alpha. I getting from the questions here, and alpha is from this one. So in the end, you will get that the value of the torque is equivalent to 31 Newton meters. Okay. Okay, now we have a very good example, the falling bucket. Okay. Okay, this is very good examples. Okay, a solid, uniform, frictionless. A solid, uniform. The solid means, okay, it doesn't have hollow inside the reel. Okay, that means it's full with the atoms of solids. Okay, solids, uniform, frictionless, cylindrical reel of mass m equals to 3 kilogram and radius 0.4 meters is used to draw water from a well. Okay, a bucket of mass 2 kilogram is attached to a cord that is wrapped around the cylinder. Find the tension T. Okay, find the tension T in the cord and the acceleration alpha A of the bucket. Okay, find the tension T. All right. Okay, right now we have a situation where we have a bucket that is connected to a cord, okay, tali, and then that has been wrapped up around a solid uniform cylindrical reel. Okay, solid uniform cylindrical reel. So this is a bucket. We have one situation, bucket, and this is reel, cylindrical reel. So normally when we try to do these examples, but in terms of only force, okay, not the torque and whatsoever in this chapter, okay, we just only focus on the summation of fx equals to okay, just fx equals to me for x and also y exists, but not the summation of torque. But in here we need to use that equations. Okay, we need to use some equations regarding especially torque equals to I alpha. Okay. Okay, try to imagine these things. Okay, this is real. Okay, and the reel is put on the some woods that hold the reel so that it can rotate easily. And of course, the reel is a solid. That means that the reel have some mass that we should consider is as mg. So this is the mass of the reel, and because it's been put on the on the wood on two wood stand, so it must have some normal force. And don't forget, okay, because the reel is being wrapped up around with the some cord. Okay, so this cord is actually a tangent. Okay, so if I can use some analogies, so this is how they wrap. So this is your bucket. Okay, so they are using the same tension. So they have two. They have a force at the bucket and also some forces at the reel. Okay, so this thing is very, very dangerous when you didn't have some imagination, or you may lack of ideas on how to put some force to the reel. Okay, so find the tension T. So this is how they get. Okay, again, okay, they may use some equation. This one is summation of F equals to MA because the bucket will go down, and of course, or maybe the bucket is it doesn't matter, but it is equivalent to MA. So you can put that okay, because this one is heating the water, so you can just mg minus t equivalent to ma. Is the bucket is falling into the water. Okay, mg minus t equals to ma. That one is considered to be one acceleration of the what they did here. Okay, they just use differently because t minus mg equals to ma. Okay, and then we have submission of torque equals to I alpha. Okay, submission of torque equals to I alpha. So what is I? Based on our knowledge in terms of a solid sphere, so it should be half mr squared alpha. Okay, and then the torque is actually, if you look carefully, this is R and this is T. T is force, so force of the torque going clockwise position. So it is a negative. Okay, a negative because it is a clockwise. Okay, clockwise position. Kalau tengok dia berpusing ke arah clockwise, so it becomes negative. So equivalent to half mr squared alpha. Okay, and then we bring all the negative and r to that part, so we can cancel out one r and also this r. So it's just left with the negative half mr alpha. Okay, remember alpha A is equivalent to R alpha, so you can replace this thing with the just A. So half MA equivalent to that part, right? So MA minus MA minus negative mg, or T minus mg, you can replace A with this value. Okay, and then you can, or you can replace T with this value. Okay, replace T because we want to find A. Okay, okay, we replace T with the negative 1 ma into this value. So now we may eliminate, just left with the acceleration equals to mg, okay, mg over m plus half m. Okay, and in the end you will get the value of acceleration that equivalent to negative 5.6 meter per second square, and replace this one. Okay, substitute the a value into this in order to get the into this part in order to get tension. The tension is 8.4 Newton. Okay, if the answer is negative or positive, just put it positive value. Okay, but in terms of acceleration, then you need to put it negative or positive. Okay, so these are the questions that can be discussed in terms of angular torque equals to I alpha. Okay, and this is the last subtopic for today, which is the angular momentum. Okay, the definitions of angular momentum. Okay, remember momentum itself is P equals to mv. Okay, our linear, is P equals to mv. That means mass times velocity. So right now, the angular momentum is L equivalent to I, okay, comparable to m omega, because V can be comparable to omega. So L equals to I omega. And the unit for angular momentum is kgm square over s. Kgm square over s. Okay, and because of that, L is equivalent to I omega. So what is I omega? This should be the equivalent to, let's say, P equals to mv. So what is V? V is m r omega. Okay, r omega, right? So r omega. So if you look carefully, is because of V equals to r omega, so you can derive P in terms of mr omega. Okay, mr omega. So that is in terms of P. But if you want to write out in terms of angular momentum, then you can use this one. Okay, L equals to I omega. So what is omega? Omega is V over R. Okay, omega is V over R. So equivalent to, okay, L equivalent to I V over R. Okay, so you can get this value up. So you can eliminate to get L equals to RmV. That is also equivalent to Rp. So if you want to see some connection between angular momentum L and also P, is you need to multiply P with some R in order to get L. Okay, so these are the um, the connection between angular momentum and also linear momentum. So the same goes as today we learn about torque equals to R alpha Rf. Okay, that means if you want to get torque, okay, angular force, so you must multiply force with the R. Okay, in order to get the angular force, or also known as torque. Okay. The angular momentum L for a point particle is Rmv sine theta. So remember, L equals to Rp. You can replace P with the M times V sine theta. Okay. And then, of course, the Newton's law, based on our Newton's law, okay, delta L over delta T, delta L over delta T is equivalent to I delta omega over delta T. So what is I delta omega over this one? Is should be alpha. So what is alpha? I alpha. I alpha is equivalent to torque. Torque equals to I alpha. So that means torque is equivalent to delta L over delta T. That means change in momentum, change in angular momentum over time, or rate of change of momentum. Okay, that's how it connects between the angular momentum and also torque. Okay, and of course, in terms of in terms of conservations of angular momentum. Okay, so I think this is the last part of the topic, which is until the angular momentum. Okay, do you have any questions? Ada soalan tak?